Precalc, Chapter 11, Section 5, Part A. So we're going to look at limits of summation, and then we're going to start using rectangles to approximate areas under curve for Part A. So this first part here, we're looking at a sum of an infinite geometric series. So we've done this first part back in Chapter 8. We're looking at a series, a summation of a sequence, a geometric sequence, and we wrote it in this form. And so the summation of 1 to infinity of the equation for a geometric sequence equals the first term divided by 1 minus r. That's what we did in Chapter 8. Now, in this chapter, we're going to use the same thing using limits to find it. The summation s is equal to the limit as n goes to infinity of the summation of 1 to n of that sequence. So the sequence of, you're adding the sum from 1 to n, and we're going to let n go to infinity. It's the same thing as that general rule. So we're going to use the limit to find that. So I just want to be able to connect it back to Chapter 8 a little bit before we start. In Chapter 8, we talk about all these formulas. So you look at the summation of a constant. So the 1 of n of a constant. So this would be like the summation of 1 of n of 2 would equal 2 plus 2 plus 2 plus dot 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 plus 2 n times. So there's n amount of 2's there. So a faster way of doing that is just doing c times n, or in our case 2 times n, to evaluate that summation. And so then we also have the summation of just I is this formula, summation of I squared and I cubed. These summation formulas we actually proved back in Chapter 8 using mathematical induction. In 5, we have some properties here. The summation of a sum or a difference can be found by doing the summation of each part and then adding or subtracting that sum. The summation for 6 here, the summation of a constant or like a coefficient of your sequence. You can pull that constant or coefficient out of the summation and multiply that constant by the summation. So a couple examples here. So let's find the summation of 1 to 25 of j squared plus j. And so we can look at this as j squared and j, so we can look at our formulas. We have j squared would be this one, and then j is this one. Those are the formulas for those. So we can find the summation of each part, the summation of 1 to 25 of j squared plus the summation of 1 to 25 of j. And so 1 to 25 of j squared, that's n times n plus 1 times 2n plus 1 all over 6, plus the sum of j is n times n plus 1 all over 2, and then we can plug in our n value. This upper bound, this is our n value. 25 is our n value. So this would be 25 times 26 times 51 all over 6 plus 25 times 26 all over 2. And then you have to evaluate that to find your sum. And so I'll let you finish that up. And the next one, we're going to actually find the summation of I cubed over n to the 4th, 1 to n. Now we don't have our n value, our upper bound. So we're going to be simplifying this formula. So in this, we have to first realize that this problem, I cubed, is what we're finding the sum of, the sequence. We have, though, a coefficient or a constant, 1 over n to the 4th. So I can pull that out in front. So 1 over n to the 4th times the summation of 1 to n of I cubed. Now I can use my summation rules for I cubed. So I cubed here is the n squared times n plus 1 squared all over 4. And so we want to simplify this. So this is 1 over n to the 4th times n squared times n squared plus 2n plus 1 all over 4. And I can reduce a little bit here. This n squared here can reduce with 2 of these in, so I only have an n squared. And so I end up with n squared plus 2n plus 1 all over 4n squared. So that would be simplified. Now at this point, in the future, we're going to be finding the limit as n goes to infinity. Problem here it would just be looking at our exponents squared. So we look at our coefficients. 1/4 would be the value if we're trying to find the limit as n goes to infinity. The red simplified rational expression here could be used to find it for any n value. If n is 10 or 50 or whatever you may want it to be. Okay, well, it's a little bit more complicated. For this one, the limit as n goes to infinity of the summation of this binomial squared times 1/n. So 1/n here again is our coefficient or our constant, and so we can pull that out in front. So we're going to find the limit as n goes to infinity of 1/n times the summation of 1 to n of that summation. And so to do this, before we find the summation of 1 to n, we actually take care of this squared term. So 2 plus I over n, that quantity squared. If I FOIL that, I get 4 plus 4I over n plus I squared over n squared. And so then we're finding the limit as n goes to infinity of 1/n times the summation of 1 to n of 4 plus 4I, and I can pull that 4n times I plus 1/n squared times I squared, which then helps me find the summation of each portion. So now we're going to do the summation and write each one. The summation 1 to n of 4 plus the constant 4/n times the summation of 1 to n of I plus 1/n squared times the summation of I squared. Then using our formula sheet, we can expand each of these summations. So 1/n, the summation of 1 to n of 4 is 4n plus 4/n times the summation of I is n times n plus 1 all over 2 plus the summation of 1/n squared times the summation of I squared, which is n times 2n plus 1 times n plus 1 all over 6. So now we can simplify a little bit here. The limit as n goes to infinity of 1/n times 4n plus, now I can reduce this n and this n here. You can also reduce this 2 and the 4, so we have a 2 there, so I distribute the 2, and I'm getting 2n plus 2. And then we can also reduce like this n with one of these n, and so on the top there, if I FOIL that, I get 2n squared plus 3n plus 1 all over 6n, because we still have an n left in the denominator there. Last thing is we can distribute this 1/n through the parenthesis. So we have the limit as n goes to infinity of 4n plus 2n plus 2 all over n plus 2n squared plus 3n plus 1 all over 6n squared, which is kind of nice because now we're trying to find the limit as n goes to infinity. So now we can use our rules. This is the first power, so the limit of that first term is 4 plus the second one into the first, we have 2/1, which is 2, plus this last one we have n squared and n squared, so I look at 2/6, which is 1/3. So if I add those, we get 6 and 1/3 as the values, the final value. We could have done a little faster up in this step in purple here. We could have looked at this purple step, and instead of doing all the simplify, we could have only looked at the values that give us the biggest degree for each term. So like the 4n, we could look at 4n is 4n squared over 2n times this n is 2n squared. And so you don't have to mess with all of the simplifying if you're finding the limit as n goes to infinity. You could look at the values to get the biggest degree to quickly see the rule for that horizontal asymptote. Okay, the last concept we need to introduce here for part A is the area under the curve. And that's kind of what the 11.5 really talks about, is how to find the area of the curve. And we use that sequence summation, or the limit as n goes to infinity, to help us find the area of the curve. So for this problem, we're going to approximate the area under this curve using 5 rectangles. And here's our function's equation: the x-axis, the x equals 0 line, and x equals 2 line. So if I first sketch those bounds, so we have the x equals 0 line, which is this vertical line. X equals 2 is this vertical line. We have the function 8 minus x squared. And so the area under the curve would be this portion underneath the curve. Now, the length here is 2. And we know we want 5 rectangles. So to figure out the width of each one, I would take my overall length here, 2, and divide it by 5. 2 divided by 5, which is like b over n, we'll use that in the future here, is going to be our width of each rectangle. So we'd have 2/5 here, and then 4/5, 6/5, 8/5, and then 10/5 or 2. Now I can represent that another way. This is 0, so this is 2/5. The next value could be 2/5 times 2. This next x value is 2/5 times 3. The next one is 2/5 times 4. And the last one is 2/5 times 5. And I want to write it in that way so you can kind of see the sequence here, where we have 2/5 times 0 times 1 times 2 times 3 times 4 times 5. So let's draw our rectangles. For our rectangles, we're going to go straight up from that x value and then straight over. Continue that for these different x values, and they would have the equal width. Mine's not drawn that accurate. So these would be the rectangles. Now notice that it's an under approximation, and it just happens that this way, if the curve is going increasing, it would be an over approximation. So we have this area that we are not including, so it's approximate. And then we also are using what we call the right hand approximation, because we're using the right hand of each of these rectangles is what's hitting our function or our graph. So that's the portion we actually are plugging in. So I'm not plugging 0 into my function. I'm plugging 2/5 and then 2/5 times 2 in the function. So to find the area of each of these rectangles, it's our width times our height, 1. Then our width times our height, 2. And our width times our height, 3. And that continues for all of these rectangles, for our 5 rectangles. So it's really like our width times h1 plus our width times h2 plus our width times h3 plus our width. There's a faster way of doing this. Instead of writing like this, I can pull out the width and say it's our width times our height 1 plus our height 2 plus our height 3 plus our height 4 plus our height 5. And that's what we're going to do in this problem. So our width is 2/5. Our height 1 is found by plugging 2/5 into the function. So our function is up here. And so I can say that's like f at 2/5. So that's what we'd be doing. And then we're going to have to add up all of those summations. So f at 2/5, and that continues on. So this is 2/5 times. So if we do that, we get 7.84 plus 7.36 plus 6.56 plus 5.44 plus, we plug 2 in there again. We're doing to get these values, we're plugging this x value into this function. So it'd be 8 minus 2 squared for the last one, which would be 4. That's how I'm getting that value there. So I have to do the summation of all that, and we get 31.2, and then take that times our width, 2/5, to find a value of 12.48 units squared. So that would be the approximate area under the curve using this method.